Today the sun above you probably seems distant and steady, warm, familiar. But there was a time when Earth drifted dangerously close to becoming nothing more than another scorched rock swallowed by that same star. Not a myth, not a what-if story. A real moment in our planet's past when delicate gravitational balances slipped and the orbit of Earth trembled. The sky brightened into a harsh white glare. Temperatures spiked. Seasons warped. And a chain of cosmic forces lined up in a way that could have pulled our entire world inward toward fire. Scientists have found the evidence scattered through ancient rocks, frozen in glaciers, even written in the scars of the moon. Clues that Earth once hovered near a point where one more push from the sun could have ended everything. Oceans would have boiled away. The atmosphere would have peeled off like smoke. Life would have vanished before it even knew what was happening. And here is the part that should make you stop whatever you are doing. The same gravitational patterns that nearly doomed Earth billions of years ago still exist today. Subtle, invisible, waiting. So whether you are watching this in your room after homework or halfway across the world scrolling on your phone under a calm evening sky, get ready. Because once you understand how close Earth came to being pulled into the sun, you will never look at sunrise the same way again. You know that strange chill you get when you realize something you thought was solid and permanent might not be as safe as it looks. Like when you see a bridge wobble or a plane wing shake in turbulence, and suddenly the world feels a little less guaranteed. Now imagine feeling that about the moon that has hung in our sky for billions of years. Steady, pale, comforting. The moon that controls the tides and lights up the night. The moon that poets write about and explorers dream of visiting. What if I told you there was a time when that moon almost slipped away forever? A moment in deep cosmic history when Earth nearly lost its only natural companion and the sky almost changed in a way no human could ever undo. It sounds impossible. The moon feels locked in place, like a giant anchor in the heavens. But the simulation glowing on Dr. Mara Ellison's screen tells a different story. She sits alone in a quiet observatory lab late at night, staring at a model of the Earth-Moon system slowly rewinding through time. At first, the orbit looks normal. The moon simply drifts inward the way physics says it should if you travel back billions of years. Then something happens. The orbit starts to stretch. It twists into a long oval. It vibrates like a struck guitar string. Then the moon swings wide, almost snapping free from Earth's pull before spiraling back inward again. Mara leans closer as the room around her fades into silence. This is not a glitch. This is not a math mistake. This is a real possibility buried in the physics of our solar system. For years, scientists believed the Earth-Moon relationship was simple. Earth spins. The moon pulls. The tides move. The moon slowly drifts away at the pace of your fingernail growing. A calm, predictable, celestial dance. Except when Mara and her team pushed their simulation far enough back, they found something no one expected. A chaotic era when the forces between Earth, the moon, and even the sun created a cosmic tug-of-war so intense the moon might have actually gained enough energy to break free. Not crash into Earth. Not fall apart. Escape. Float away into the darkness as a lone wanderer leaving Earth behind forever. Picture that. A world without lunar tides guiding ancient oceans. A world without a stabilizing force holding Earth's tilt steady. A world where evolution, weather, and maybe even life itself turned out completely different because the moon did not stay. Mara watches the simulation rewind further. The glowing moon swings again off its normal path. She feels her heart race. This is the kind of discovery that changes textbooks. It overturns what we thought we knew about our own sky. Because the truth is that nothing about the Earth-Moon system was guaranteed. not its creation, not its orbit, not its survival. Our moon did not simply appear and settle into place like a light bulb in a socket. It fought to stay. It survived conditions that could have sent it drifting away long before humans ever looked up. And as the simulation resets and runs forward again, Mara whispers to herself words that no one ever thinks to say about the moon. We almost lost you. If you look at the moon long enough, you start to feel like you know it. It rises and sets. It shows the same face every night. It drifts across the sky at a pace so steady it feels almost timeless. But scientists learned long ago that if you watch something closely enough, tiny details start to whisper secrets. And the moon has been whispering for decades. At first, the clues seemed harmless. Slight wobbles in the moon's rotation that did not match predictions. A small but stubborn mismatch between where the moon should be according to simple physics and where it actually is. The numbers were off by just a little, but that little was enough to bother people who make careers out of measuring the universe down to the millimeter. You would think fixing the model would be easy. Earth spins. The moon orbits. Tides happen. Energy moves around. End of story. Except it was not the end at all. Every time scientists added new data, the same thing happened. The moon's behavior did not perfectly match the model, as if something important had been left out. Something big, something ancient. Dr. Mara Ellison knew this irritation well. For years, she had stared at the data with the same nagging feeling you get when you hear a sound in your house at night and cannot explain it. It is probably nothing. But what if it is not nothing? The strange part was that the moon's orbit was too smooth for a world with such a violent history. Everyone knew the moon formed after a collision so massive it turned Earth into a boiling sea of magma. Everyone knew its early orbit must have been wild. Yet the models could not recreate the moon we see today unless they made early Earth and early moon too calm, too gentle, too simple. Something did not add up. And that is where the first real breakthrough came from. A graduate student running a simulation noticed that when he added a tiny correction to the moon's orbital eccentricity, the entire model suddenly snapped into better alignment. It was like tugging one thread in a huge knot and feeling the whole thing loosen. That tiny correction was a clue. A sign that for a brief moment, somewhere deep in the past, the moon's orbit had stretched more than scientists expected. Not by a huge amount, but by enough to leave a fingerprint that survived for billions of years. A cosmic bruise, the kind that does not fade completely. Mara and her team began digging into that bruise. If the moon once moved in a more stretched orbit, something must have pushed or pulled it. Something that changed how it rotated. Something that forced it into a wobble pattern the simple models never predicted. Something powerful enough to leave a permanent scar in the moon's motion. As the team dug deeper, the mystery grew. Every new data point pointed to the same unsettling conclusion. The early Earth-Moon system was not calm at all. It was teetering on the edge of chaos. Forces were pushing and pulling in ways no one had fully understood. And the moon was reacting in ways no model could explain. Not until they discovered the resonance. The hidden timing trick buried in the dance between Earth, the moon, and the Sunday. The clue that finally revealed how close the moon once came to breaking free. Scientists had not just found a weird orbit. They had found the faint echo of a near disaster written into the sky. Most people think of time as something that only moves forward. Days pass, seasons change, the moon rises and sets. But in a quiet lab filled with humming servers and glowing screens, a team of planetary dynamicists decided to do something nature never allows. They chose to run time backwards, not with magic, with math so heavy it needed supercomputers the size of rooms. They called it rewinding the cosmic tape. It started simple. Feed in everything scientists know about Earth today. Its mass, its spin, its tides. Feed in everything known about the moon, its distance, its pace, its slow drift outward. Then press rewind and watch the numbers unfold in reverse. At first, the simulation behaved exactly as expected. The moon drifted inward at the same rate it normally drifts outward. Centimeters turned into meters. Meters turned into hundreds of meters. Earth's day grew shorter minute by minute. None of this was surprising. This was the part of the universe everyone already understood. But the deeper the team went, the stranger things became. After a few 100 million years, the moon's orbit began to tilt in ways the simple theories never predicted. The path stopped looking like a neat oval and started looking stretched and nervous, like it was being pulled by something invisible. Mara Ellison sat behind the main console, eyes locked on the spiraling dots on the screen. There was a moment about 1 billion years back when the moon suddenly wobbled. Not a cute little wobble, a sharp jolt as if something tugged on it with real force. The room went silent. The simulation kept running. The moon moved closer to Earth. Closer still, the numbers were unmistakable. They were entering a region of gravitational behavior scientists usually avoid because the math becomes unstable. Tiny changes can explode into giant differences the same way one wrong step can send a tightrope walker swinging into the air. But that instability was the whole point. Hidden inside chaos might be the answer to the moon's strange orbit. So the team pushed the simulation deeper into the past. 500 million years. 700 million. 900 million. The moon's path twisted wildly. It leaned one way, then snapped back the other. It spun faster. It drifted inward in sudden jolts that made no sense unless some long-forgotten force was acting on it. One researcher whispered that they were entering the danger zone, the region where the moon was no longer safely tucked inside the calm gravitational pocket Earth keeps it in today. This was a time when the moon might have been close enough to feel the full pull of Earth's tides and the full shove of the sun's gravity at the same time, a terrible combination. Too much push in the right rhythm and the moon could have broken loose. Too much pull and it could have fallen back toward Earth. Watching the simulation felt like watching a cliffside crumble in slow motion. You know something dramatic happened. You just do not know when the final piece will fall. As the moon spiraled even closer to that ancient chaotic domain, the room grew quiet. The team realized they were seeing a moment no human had ever witnessed. A moment when the moon's fate was not settled. A moment when escape was not just possible but frighteningly close. And they were only just beginning to understand what force pushed it there. 4.5 billion years ago, Earth was not the calm blue world we know. It was a young planet still growing, still crashing into anything unlucky enough to cross its path. Space back then was crowded and violent, filled with leftover debris from the birth of the solar system. And in that chaos, something happened that should have ended Earth before it even began. A wandering protoplanet, about the size of Mars, now called Theia, slammed into Earth with a force no human can truly imagine. The impact was so powerful, it turned both worlds into a single, shared firestorm. Mountains evaporated, oceans of rock boiled. The surface of Earth became a rolling sea of lava glowing brighter than any sunrise. For a moment there was no sky, only vaporized stones swirling in space. The crash did not just break Earth. It tore off a huge chunk of it, hurling molten rock and metal into orbit. That debris did not float peacefully. It formed a raging ring of fire around the shattered young planet, spinning so fast that every piece smashed into every other piece, over and over again. Think of billions of collisions happening each second, each one throwing sparks of molten rock across the void. That was the birthplace of the moon. But here is the part most people never hear. That newborn ring was wildly unstable. It was not a perfect circle. It was jagged, stretched, twisted by gravity and chaos and leftover shockwaves from the impact. If you could have stood on the molten Earth and looked up, you would not see a glowing disk forming neatly in the sky. You would see a storm of blazing rocks whipping around the planet at speeds that would tear a normal world apart. Some pieces slammed together and stuck, others smashed into dust. Some were thrown back down to Earth like fiery comets. The early moon was not created in a gentle drift. It rose out of chaos and violence, like a survivor crawling out of an explosion. The first clumps that would later become the moon formed quickly, but they had no guarantee of staying together. Gravity was fighting to pull them into a sphere. Thermal pressure was pushing them apart. And Earth's own gravity was tugging at the edges of the disk so hard that entire chunks threatened to fall inward and melt back into the young planet. Even more unsettling was the constant battle between the disk and the Sunday. Because Earth was still fresh from impact, its orbit wobbled. That wobble meant sunlight hit the debris ring unevenly, heating some parts more than others. Hot materials expanded and drifted outward. Cooler parts clumped inward. This constant push and pull turned the ring into a churning spiral that could have easily ripped itself apart. In many simulations, the moon never forms. The ring collapses. The pieces scatter. Earth ends up moonless and unstable. But in our timeline, something rare happened. Amid all the chaos, the debris slowly gathered into a single growing body. A glowing sphere formed in the sky, still molten and furious, but held together by gravity that barely managed to overpower chaos. That sphere was the first version of the moon, and even then its survival was not guaranteed. It still had to stay in orbit around a broken world that was far from done shaking. And the young sky above Earth had no idea that the moon it had just formed would almost slip away forever. Imagine looking up at the sky and seeing the moon so close it fills half the horizon. Not a calm silver disk, but a boiling orange world still glowing from the heat of its own creation. That was Earth's reality in the days after the impact with Theia. The young moon was only a few tens of thousands of kilometers away, closer than some satellites are today. It hung in the sky like a giant wound in space, pulsing with heat and light. Below it, Earth was no better. The surface was a rolling ocean of magma stretching across the entire planet. No continents, no oceans, just endless molten rock swirling under a thick atmosphere of steam and vaporized minerals. The heat was so intense the sky shimmered red. The early moon circled this world quickly, completing an orbit in only a few hours, and Earth spun even faster. A day back then was not 24 hours, it was more like 5. The planet turned so rapidly the horizon never stopped racing. This created a gravitational storm between Earth and the moon, unlike anything that exists today. Tides rose not by a few meters but by kilometers. Enormous waves of molten rock sloshed around the planet, pulled upward by the moon's gravity. Every time the moon passed overhead, it dragged Earth's magma upward like a giant hand gripping the surface. Then, as Earth spun faster than the moon orbited, the tidal bulge raced ahead of the moon and yanked it forward, giving it extra energy. That push made the moon climb higher into orbit, inch by inch. This delicate transfer of energy is what eventually moved the moon away from Earth to the safe distance we see now. But in the beginning it was anything but safe. Back then the system was incredibly unstable. The moon was so close that one wrong shift in Earth's rotation, or one strong gravitational nudge, could have changed everything. If the tides pushed too hard, the moon could have spiraled outward too quickly and snapped free of Earth's pull. If Earth's rotation slowed too fast, the moon could have fallen inward and collided with the planet in a second cataclysm. Scientists call this region the danger zone, and the moon lived inside it for millions of years. Imagine a tightrope stretched across a pit of fire. The early moon walked that rope with every orbit. A little too much outward energy, and the rope snaps. A little too much inward pull, and the water falls. Even small changes to the magma ocean could shift the entire balance. Hotter magma meant stronger tides. Stronger tides meant bigger pushes. And a few extra pushes at the wrong moment could fling the moon onto an escape path. Meanwhile, the moon itself was cooling and shrinking, cracking on the surface as it lost heat to space. That cooling changed how it reacted to Earth's pull. Some nights it sped up, some nights it slowed down. Even the slightest change in shape could alter its orbit. This was not a peaceful relationship. It was a struggle between gravity, heat, and rotation, with the fate of the entire Earth-Moon system hanging in the balance. The only reason the moon survived was because somehow every chaotic push balanced every dangerous pull. Over millions of years, the moon drifted out of the danger zone inch by burning inch. But in those early ages, when it hovered low above a molten world, nothing about its future was guaranteed. It was a survivor in a sky where anything could have happened, and almost did. If you step outside on any clear night and look at the moon, you will notice something strange. No matter when you look, no matter where you stand on Earth, you always see the same face, the same craters, the same dark seas, the same frozen expression staring back at you across the sky. It feels normal because it has always been that way for humans. But the story of how the moon got stuck like that is anything but normal. It is a story about gravity fighting rotation and a dangerous dance that almost went wrong. In the early days after the moon formed, it spun quickly. It twirled like a figure skater fresh off a jump, showing every side to Earth as it circled overhead. But this spinning moon was orbiting a world covered in magma and violent tides. Every time the moon passed over Earth's molten surface, it raised massive tidal bulges. Those bulges had weight, and they tried to pull back on the moon. They tugged at its spin, slowing it a tiny bit each time. It was like the moon was trying to keep turning, while Earth kept grabbing its arm and telling it to slow down. Over millions of years, that constant pull drained the moon's rotation until something incredible happened. One day the moon turned at the exact same rate it orbited Earth. That meant the same side was always facing downward. At that moment, the tugging stopped. The tidal friction dropped. The system suddenly calmed. The moon had entered tidal lock, but here is the part most people never hear. That outcome was not guaranteed. The early Earth-Moon system was so unstable that even tiny changes could have prevented tidal locking from happening when it did, or at all. If the moon had cooled a little slower, its crust would have been softer and the tidal forces would have acted differently. A softer moon might have kept spinning longer. If Earth's magma ocean had lasted a bit longer, the tides could have been stronger and pulled the moon into a wobbling spin pattern instead of a clean lock. In some simulations, the moon ends up trapped in strange rotations where it shows different faces at different points in its orbit. In others, it slips into what scientists call chaotic tumbling, where its orientation flips unpredictably like a toy thrown into the air. A moon that tumbles cannot stabilize Earth's tilt. A moon that spins irregularly loses energy in the wrong way. And a moon that does not lock can fall into orbital patterns that lead to escape. The tidal lock we see today is a very narrow solution to a very messy problem. When the moon finally became locked, its rotation lined up with its orbit in a perfect balance point. Gravity pulled just enough. The moon resisted just enough. The system settled into a calm rhythm, and that calm let the moon continue drifting outward safely. If that moment had not happened exactly when it did, the moon might have spun itself into an unstable orbit or fallen into a resonance that flung it away from Earth entirely. Instead, the gravity dance ended with a kind of cosmic handshake. Earth slowed the moon's spin, and the moon stabilized Earth in return. And that quiet face, staring down at us every night, is not a symbol of peace. It is the frozen pose of a survivor that almost lost the dance. There are moments in science when a discovery feels less like new information and more like finding a hidden trapdoor under your own floor. That is what happened the first time researchers noticed something strange buried deep inside the simulations of the early Earth-Moon system. The Moon's orbit was not just reacting to Earth, it was reacting to the Sun in a way no one had fully understood. It was a resonance, a kind of cosmic rhythm where two different motions line up just right and start feeding energy into each other. And this hidden resonance was powerful enough to almost tear the Moon away. Resonances happen everywhere in nature. A swing pushed at the right moment goes higher. A bridge shaken at the right frequency can collapse. But when you discover a resonance in the motions of worlds, it becomes something far more dangerous. In this case, the rhythm appeared when the Moon's orbit around Earth synced up with the timing of Earth's orbit around the Sunday. For a brief but critical window in deep time, every time Earth went around the Sun, the Moon hit a point in its orbit where the Sun's gravity tugged in the exact direction needed to stretch the orbit a little more. One tug does nothing. 1,000 tugs change everything. When Dr. Mara Ellison and her team saw the pattern appear on their screens, they leaned in closer. The Moon's orbit was becoming longer and more elliptical. That meant the Moon was speeding up in some places and slowing down in others. And every time it slowed, the Sun grabbed hold and pulled harder. It was like watching someone climb a ladder only to have the Sun keep adding rungs underneath. One researcher described it as a lever. Earth's gravity was the pivot, the Sun was the force, and the Moon was the object being lifted into a higher and higher orbit. If the resonance had lasted a little longer, the Moon could have gained so much orbital energy that it would drift to a distance where Earth could no longer hold it. Just a small change in timing, and the Moon would have escaped, becoming a lonely object wandering through the solar system. The wild part is that the resonance was not obvious. It was not visible in the sky today because it stopped long before humans existed. The only reason anyone found it is because modern computers are finally strong enough to simulate the Earth-Moon-Sun system with insane detail. When the team ran thousands of versions of the past, the same dangerous pattern appeared again and again. In some simulations, the resonance grew so strong the Moon spiraled outwards so fast that escape became unavoidable. In others, the Moon's path twisted into such a strange shape that Earth's rotation wobbled out of control. Only in a narrow set of timelines did the resonance break naturally before disaster happened. That thin path is the one our world took. When Mara replayed the simulation in slow motion, she saw it clearly. The Moon's orbit stretching like a rubber band. The Sun tugging at the exact point where Earth could not counter it. And the whole system trembling from the strain. The hidden resonance had almost rewritten the history of our planet. It had come close to breaking the bond between Earth and Moon forever. And the most unsettling part was realizing that the only reason we have tides, seasons, and a stable climate today is because that cosmic lever stopped pulling at the last possible moment. If you have ever pushed someone on a swing, you already understand the basic idea behind one of the most dangerous forces the Moon has ever faced. A swing only goes higher if you push at the perfect moment. Too early or too late and nothing happens. But hit the rhythm exactly, and each push adds more and more energy until the swing reaches heights it was never meant to. Now replace the swing with the Moon. Replace your hand with the Sunday, and replace the gentle back and forth with a violent gravitational rhythm called evection. That is the cosmic slingshot that almost threw the Moon away. The evection resonance is one of those phenomena that sounds tiny and harmless when you describe it with equations, but becomes terrifying when you imagine it happening in real space. Picture the young Earth turning quickly under a still, cooling Moon. The Moon's orbit is stretched and unstable from the chaos of its birth, and far beyond both of them, the sun pulls with a gravity that never stops. Most days, the sun's pull and Earth's pull do not line up in a meaningful way. They tug in different directions, and the moon stays locked in Earth's grip. But there was a time long ago when the moon orbited at just the right distance, and Earth took just the right amount of time to go round the Sunday. In that window, something dangerous happened. The sun's strongest pull began lining up with the moon's slowest point in its orbit over and over again. Every orbit the sun nudged the moon at the exact right moment. One nudge did almost nothing. A few dozen nudges made a small stretch, but thousands of perfect nudges in a row turned the moon's path into a wildly elongated shape. The orbit grew like an overstretched loop of rope. The moon shot farther from Earth each month and took longer to swing back around. And the farther it got, the easier it became for the sun to tug again. Imagine watching the moon at that time. Instead of a smooth circle around Earth, it would swing out wide into deep space, then dive back in close like a comet visiting from across the solar system. With every cycle, the sun's gravitational push grew stronger while Earth's grip weakened. It was a slow, quiet battle, but a battle Earth was on the verge of losing. Scientists studying the simulations could see the danger unfolding. When the moon reached the peak of its stretched orbit, the sun almost stole it. The orbital energy was rising. The bond between Earth and moon was thinning. One more increase in stretch and escape would have been guaranteed. The moon would drift outward until the sun claimed it completely. Earth would be left spinning alone, with no tides and no stabilizing force to hold its tilt steady. The evection resonance was not a gentle event. It was a cosmic slingshot winding up with more power than the early Earth-Moon system was ever built to handle. In many simulated timelines, the slingshot does not stop. The moon flies free into the darkness. But in our timeline, something rare happened. The resonance broke. Earth's rotation slowed just enough. The moon drifted far enough. The sun's rhythms slipped out of sync, and the cosmic slingshot lost its aim. The moon stayed, but it was a near miss. A close call, measured not in meters but in cosmic timing. A different rhythm, and the sky above us would be forever empty. When the research team finally pushed their supercomputers to run thousands of full Earth-Moon simulations, the screens filled with timelines that looked less like science and more like alternate universes. Each simulation was a different version of history, shaped by tiny changes in temperature, rotation, timing, or gravitational nudges that would have been impossible for any living creature to notice. But those tiny changes created outcomes so wildly different that the room fell silent as the results poured in. In one simulation, the moon drifted outward just a little faster than expected. At first it seemed harmless. Then the evection resonance locked in a bit longer, and the sun tugged at the moon with perfect timing. Within a few million years, the orbit stretched so far that Earth's gravity could not pull it back. The moon left. It simply drifted away into the cold darkness until it became nothing more than a faint wandering body lost somewhere between Earth and Mars. In another simulation, the opposite happened. The moon started wobbling more sharply than it should have. That wobble changed how it reacted to Earth's tides. Instead of drifting safely outward, the moon stalled, then fell slightly inward. Just a small drop, but enough to pull it into a dangerous spiral. The tidal forces grew stronger and stronger until the simulation ended in a fiery collision as the moon slammed into Earth, turning the planet into a molten wasteland all over again. Some simulations ended even stranger. A few showed the moon breaking into pieces after passing too close to Earth during a resonance spike. The fragments formed a brief ring like Saturn, except glowing red from the heat of destruction. Other simulations showed Earth's tilt wobbling uncontrollably without a stable moon to steady it, leading to wild climate swings that made long-term life impossible. Every version was a reminder of how fragile the early system truly was. But then came the rarest simulations, the ones that looked like our universe. In those timelines, the moon drifted outward at just the right pace. The resonance locked in, but not too deeply. Earth's rotation slowed at the perfect rate. The sun tugged, but then slipped out of sync before things went too far. It was a cosmic tightrope walk. Too much pull, and the moon escaped. Too much inward drag, and it fell. Only a razor-thin path allowed the moon to survive without destroying either itself or Earth. Mara Ellison stared at that narrow band of safe outcomes glowing on her monitor. It looked like a tiny sliver in a forest of disasters. A thin line where everything balanced for no clear reason except luck and physics weaving themselves into a fragile truce. What struck the team hardest was how easily our timeline could have been different. One slightly hotter magma ocean, one slightly faster early rotation, one tiny variation in the moon's early shape. Any of these could have pushed the system into a different branch of fate. The simulations were not telling a simple story. They were showing that our moon is not just a leftover rock in the sky. It is a survivor. A lucky winner in a universe filled with timelines where it did not make it. And the path that led to our real world was not wide or obvious. It was thin, almost impossibly thin. Yet it was the one path that gave us the moon we see today. You stand on a shore that should not exist. A strip of half-solid rock trembling between a glowing magma ocean and a sky filled with choking steam. The air burns your lungs with every breath. The ground quivers beneath your feet like it is alive. You wipe ash from your eyes and look upward, and that is when your brain freezes. Hanging above you is the moon, but not the moon you know. This one is enormous, a monstrous sphere so close it fills almost the entire sky. It glows a deep orange red from trapped heat, streaked with rivers of molten rock crawling across its surface. It looks less like a moon and more like a newly formed world struggling to survive. You cannot look away. The moon's pull is unbelievable. You feel it in your bones. The magma ocean behind you is not calm. It heaves upward, pulled by the moon's gravity into a wave taller than mountains. You watch the glowing liquid rock lift and twist as if reaching for the moon. When the tide falls, the entire shoreline cracks with thunder, sending fountains of lava bursting upward. The heat on your face is like standing beside a furnace the size of a continent. Even the ground beneath you shivers from the stress. Earth is spinning far faster than it will in the distant future. A day lasts only a few hours, and the horizon races by as if the planet is trying to run from its own destruction. Because Earth spins so fast, the tidal bulge formed by the moon is always ahead of where the moon actually is. That bulge tries to drag the moon forward. You can almost imagine the planet shouting with effort as it pulls upward on the moon, trying to send it farther away so the tides will weaken. But the moon pulls back. Every time it passes overhead, the rock beneath you rises, cracks, and collapses. Every orbit sends a violent shudder through the young planet. You feel it in your legs like a heartbeat too big for the world to hold. You watch as the moon circles above you again. It does not drift lazily across the sky. It moves fast, crossing from horizon to horizon in only a few hours. The light it casts is not gentle. It blazes like a second sun, painting the magma ocean in ripples of gold and blood red. Shadows stretch long and sharp across the broken ground. When the moon reaches its closest point, the gravitational pull becomes almost unbearable. The rock under your feet seems to stretch. The horizon warps. You feel your balance shift as if the world itself is tilting beneath you. For a terrifying moment, you wonder if Earth might tear apart completely. You glance again at the moon, and for a split second it looks like it is slipping away, climbing higher in the sky. Then the orbit swings inward again, and the massive glowing sphere rushes back across the horizon, dragging the tides with it. The Earth-Moon system is locked in a struggle so intense it feels like the universe is holding its breath. You are standing in the middle of a cosmic battle, a world trying to slow its spin, a moon trying to rise. Gravity pulling at everything until the crust groans under the strain. You do not belong here. No human does. Yet you stand on that molten shore watching a sky that looks moments away from breaking. And deep inside you know the truth. If the balance shifts even slightly, Earth will lose the moon forever, or be torn apart trying to keep it. When people talk about the moon drifting away from Earth, they usually imagine something calm and steady, like a boat floating from shore on a gentle tide. But in the early days of our planet, nothing about that drift was gentle. The entire process depended on how energy moved between Earth and the moon, and that movement was driven by violent forces carving through oceans of magma and crust, still trying to solidify. If you want to understand how close the moon came to escaping, you have to picture energy not as light or heat, but as something almost alive, shifting between two worlds, locked in a constant pull. In the beginning, Earth spun so fast, its days were only a few hours long. That rapid spin created massive tidal bulges in the oceans of molten rock. These bulges did not sit quietly under the moon. Instead, they were dragged forward by Earth's rotation, racing faster than the moon could orbit. When those bulges moved ahead, they grabbed the moon with their gravity and yanked it forward. That pull added energy to the moon's orbit, and every bit of added energy pushed the moon farther away. This is where the real danger lived. The more energy the moon gained, the easier it was for it to slip into stretched orbits where the sun's gravity could shove it even harder. And all of this came down to how quickly Earth was losing its own rotation energy. The magma ocean controlled everything. Thick molten rock meant stronger tides, and stronger tides meant more drag, more energy transfer, and more outward push on the moon. If the early oceans stayed molten for too long, the moon would have rocketed outward far faster than it should. In some simulations, it gained so much energy so quickly that it reaches the edge of Earth's gravitational hold and breaks free. But the opposite danger was just as real. If Earth cooled too fast and a crust formed early, the tides would weaken. Weak tides would fail to pull the moon forward, and without that forward pull, the moon could begin to spiral inward. The closer it came, the stronger Earth's gravity would become, until the moon's orbit collapsed and the two worlds collided in a second planet-destroying impact. Earth was stuck between two disasters. Too much tidal energy, and the moon escapes. Too little tidal energy, and the moon falls. The only safe path was incredibly narrow. As Earth slowly cooled, the magma ocean thickened and cracked until a crust finally formed. That crust dampened the tides just enough to slow the runaway energy transfer, but not enough to trap the moon in a death spiral. Earth's rotation slowed from hours to days. The moon drifted outward, but not too quickly. For the first time since the giant impact, the system began to settle. But even then, everything remained fragile. Deep beneath the crust, molten rock still churned, and every shift in that churning affected the tides. Every tide affected the moon's drift. Every tiny change in the moon's drift either kept it safe or pushed it closer to the edge of escape. At this stage, the fate of the moon depended entirely on the balance between Earth's slowing spin and the moon's rising orbit. It was a delicate tug of oceans and rock, a constant exchange of energy where one wrong adjustment could have changed the sky forever. And the most incredible part is that even with all the danger, Earth and the moon somehow found the one path that kept them together. That fragile balance is the reason the moon is still hanging above us instead of drifting alone through the darkness. There is a moment buried deep in the early history of Earth and the moon that scientists now call the first great narrow escape. It does not appear in the sky. It does not leave a mark on the surface. You cannot see it with a telescope. But inside the simulations that rewind billions of years, there is a point where the moon drifts so close to the edge of escape that the entire future of our planet hangs on forces smaller than a heartbeat. To understand this moment, you have to imagine the Earth-Moon system as a pair of dancers moving on a floor that keeps shifting under their feet. Every spin of Earth sends tidal energy into the moon. Every orbit of the moon pulls energy back out of Earth. At first, this exchange is wild and unbalanced. But as the moon moves farther away, the system begins to calm, at least on the surface. What the simulations revealed, however, is that the calm is only an illusion. As the moon climbed to a specific distance, something unexpected happened. A threshold appeared. A point where the moon no longer drifted outward gently, but instead began to react strongly to even the smallest changes in Earth's tides. In the simulation room, Mara Ellison watched the critical distance appear in glowing numbers across the screens. When the moon reached that distance, its orbit stretched dramatically, not by a little, by enough that its far point in orbit pulled dangerously close to the sun's stronger gravity. It was as if the moon had reached a mountain ridge high above a valley. One small step forward and it would fall toward escape. One step back and it would slide into safety. The ridge was narrow, narrower than anyone expected. In many of the simulated timelines, the moon received just a little too much energy at this point. A slightly stronger tide from a hotter patch of Earth's mantle, a tiny change in the shape of the young crust, a shift in how fast Earth rotated during that period. Any of these could add the amount of orbital energy needed to push the moon past the ridge. Once past it, escape became inevitable. Earth's gravity would be too weak to pull the moon back. The moon would drift out of the islands of stability and into the open sea of solar gravity. But in another branch of the simulations, the opposite danger hit. If the moon received slightly less energy during this period, its orbit did not stretch enough. The moon lingered too close to Earth, where the tides remained dangerously strong. That left it vulnerable to an inward spiral. The ridge between escape and collapse was terrifyingly thin. Only a very small range of tidal strength allowed the moon to pass this threshold safely. When the team layered all the simulations together, a pattern emerged. There was a distinct bottleneck in the early evolution of the Earth-Moon system, a point where the system had to pass through a narrow gravitational gateway, too much energy, and the moon leaves forever. Too little energy, and the moon falls inward toward destruction. Only a few % of the simulations found the perfect middle ground, and our world came from one of those rare cases. The moment the moon drifted beyond that ridge, the entire system relaxed a little. The orbit became rounder, the tides became gentler, Earth's rotation slowed just enough. It is hard to believe that the survival of something as grand as the moon came down to such a delicate balance. But that is exactly what the first great narrow escape was. A razor-thin pass through a cosmic doorway. A doorway that almost closed on us forever. The early Earth-Moon system was already unstable on its own, but what the simulations revealed next made the entire story feel even more unreal. Earth and the moon were not fighting this battle alone. Other planets were interfering, planets that had no idea they were shaping the fate of our sky. Jupiter, the giant of the solar system, and Venus, the bright morning star, became silent troublemakers. They never touched Earth directly. They did not collide or approach dangerously close. Instead, they did something far more subtle and strangely more powerful. They warped Earth's orbit by the smallest amounts. Changes so tiny you would never notice them by looking at the sky. But when the moon was trapped in the dangerous resonance that almost launched it into deep space, those tiny nudges became huge. Imagine Earth orbiting the sun, like a runner on a track. Now imagine a giant standing outside the track, taking long, slow breaths. With every breath, the air shifts just slightly, changing the runner's stride. That is what Jupiter did. Its mass is so enormous that its gravity reaches across hundreds of millions of kilometers. Every time it moved in its orbit around the sun, it tugged gently on Earth. Not enough to throw Earth off balance, but enough to stretch and squeeze Earth's path in a slow, repeating rhythm. Venus played its own role. Even though it is much smaller than Jupiter, it travels much closer to Earth. Its gravity added a second rhythm to Earth's orbit. Together, the two planets created a combined pattern that made Earth speed up or slow down around the sun by tiny amounts. That alone sounds harmless. But when those rhythms lined up with the moon's stretched orbit, the entire Earth-Moon system behaved like a machine built from glass gears. One wrong shift and the whole thing could shatter. In Mara Ellison's simulation room, people watched these influences ripple through the orbital models. When Jupiter pulled a little harder, Earth moved ever so slightly faster around the Sunday. That changed the timing of when the moon reached the spot in its orbit where the sun tugged most strongly. A tiny shift in timing, but enough to amplify the dangerous resonance that stretched the moon's orbit. If that resonance grew even a little stronger, the moon would have swung too far outward and escaped. The terrifying part came from Venus. When its orbit lined up just right, it pushed Earth's timing the other way. That moved the dangerous tug to a different point in the moon's orbit. Suddenly the sun was pulling at the wrong moment, creating chaos instead of escape. In those simulations, the moon's path jolted and twisted. In some of them, the moon dropped inward toward Earth instead of drifting outward. Jupiter and Venus were not trying to cause trouble. They were simply following the laws of gravity. But gravity does not care about the risks. What the team realized was chilling. The moon's survival depended not only on the balance between Earth and the moon, but on the entire solar system staying just right. The planets formed their own background music, and the Earth-Moon system danced to that rhythm whether it wanted to or not. When the music lined up the wrong way, the resonance grew strong enough to threaten everything. When the music slipped out of sync, the danger faded. It was chance, pure cosmic chance. A solar system acting like a delicate machine where the slightest adjustment changed the final result. Without Jupiter, the resonance might have been weaker. Without Venus, it might have lasted longer. Without this exact arrangement of planets, the moon might not be in our sky. The more the team studied, the more they realized how absurdly lucky the Earth-Moon partnership truly is. If you ever look through a telescope at the moon, you will notice it is covered in scars, deep round craters with sharp rims, vast basins that look like bruises frozen in stone. To most people, they are just marks on a distant world. But to scientists, those craters are witnesses. They are the moon's memory etched into its surface. Every crater tells a story about the time when the solar system was young and violent and unpredictable. What the simulations showed is that the moon's most dangerous orbital periods lined up with some of the most intense bombardments in its history. When Mara Ellison and her team compared the timing of their models with the ages of the moon's largest craters, they felt a shock of recognition. The scars matched the chaos. Billions of years ago, the solar system was filled with leftover debris from planet formation. Asteroids and protoplanets drifted through space with unstable orbits. Sometimes they crashed into each other. Sometimes they grazed planets and moons. And sometimes they slammed full force into whatever stood in their way. Earth was hit. Venus was hit. Mercury was blasted into its odd metal-rich form. But the moon recorded the impacts more clearly than any of them because it has no atmosphere, no weather, and almost no geological activity. Nothing erases its scars. That means the moon carries a perfect record of ancient destruction. And some of that destruction happened during the exact moments when the moon's orbit was at its weakest. One of the most dramatic examples is the formation of the South Pole Aitken Basin. It is one of the largest impact craters in the entire solar system, a wound so deep it punched into the moon's lower crust. Radiometric dating places it close to a time when the moon's orbit was stretched by tidal energy and solar resonance, making it more vulnerable to gravitational nudges from passing objects. Another cluster of major impacts lines up with the late heavy bombardment, a period when the orbits of the giant planets shifted, causing swarms of asteroids to scatter inward. The simulations showed that around that same era, the moon's orbit passed through another unstable region, where a small gravitational push could have sent it closer to or farther from Earth than was safe. When Mara overlaid these timelines on her screen, she realized something incredible. The moon was not just dealing with Earth's tides and the sun's rhythm, it was being shaken by the entire solar system. Every time a large object passed nearby, its gravity pulled on the moon. Those pulls were tiny, but not tiny enough. When the moon's orbit was already stretched thin, a small tug could shift the path in ways that made the resonance stronger or the tides more extreme. In some simulated universes, a major impact changed the orbit just enough to send the moon drifting toward escape. In others, the impact nudged the moon inward toward a slow, fatal spiral. But in our timeline, the moon absorbed the hits. It kept its orbit even while its surface shattered. It endured bombardments that would have destroyed smaller moons. It survived moments when the combined forces of gravity and collision almost overwhelmed the narrow path that kept it bound to Earth. Standing on the moon today, you would see seas of craters layered one on top of another. They are not random. They are chapters of a story about chaos and survival. They are proof that the moon lived through an age when every force in the solar system seemed determined to tear it away. Yet through all of that, it stayed, a cratered witness to a history that could have gone countless other ways. If you want proof that Earth once spun like a wild top, you do not have to search the sky. You just have to look at very old rocks. Some of the most ancient fossils on Earth are not bones or shells or anything that once walked or swam. They are patterns, tiny repeating grooves, rippled layers of stone, even growth rings left behind by simple living things that never knew they were recording the rhythm of the planet itself. These fossils are timekeepers. They hold the memory of days so short they barely resemble the 24-hour cycle we live with now. And when scientists studied them, they found something almost unbelievable. The records inside those ancient stones matched the exact periods when the moon's orbit was the most unstable. Long before humans existed, long before plants or animals spread across the land, Earth spun so quickly that a single day passed in only a handful of hours. You can see this in stromatolites, which are layered structures built by microbial mats billions of years ago. These layers are stacked in repeating patterns shaped by the tides. The distance between each layer tells how often the tide rose and fell. When scientists counted them, they found far more tides per year than expected. That only makes sense if Earth's days were much shorter and the moon was much closer. It was like reading a calendar written by creatures far too simple to understand what they were recording. Some ancient corals from much later in Earth's history also recorded daily growth lines. Each day, they added a thin band of calcium carbonate. When researchers sliced these fossils open and counted the bands, they discovered that hundreds of millions of years ago, there were more than 400 days in a year. Not because the year was longer, but because the days were shorter. Earth was spinning faster because the moon had not yet slowed it as much as it has today. These fossils do not just show that days were shorter, they show when days were shortest. Those moments line up perfectly with the periods when the moon was passing through resonant zones where its orbit stretched dangerously. The faster Earth spun, the stronger the tides became. Stronger tides meant more energy transferred to the moon. More energy meant a faster outward drift. And the faster that drift, the higher the risk of escape. When Mara Ellison compared fossil calendars with her simulation results, she felt a chill. The data matched almost too well. Every time the simulations predicted a dangerous rise in the moon's orbital energy, the fossil record showed a spike in tidal activity. Every time the models showed the moon moving through a risky orbital zone, the rock record showed Earth spinning fast enough to fuel the instability. It was as if Earth itself had written a warning note in stone and buried it for billions of years. These fossils became proof that the near disasters seen in the simulations were not just mathematical artifacts. They were real events recorded in the daily lives of ancient organisms. Creatures that lived and died without ever knowing they were marking the rhythm of a world that was barely holding on to its moon. Today, when you look at a piece of ancient coral or a layered stromatolite, you are not just looking at a fossil. You are looking at a clock. A clock that counted the days of a world spinning too fast for comfort. A clock that survived long enough to reveal how close Earth once came to losing the moon forever. Imagine standing on a planet that looks almost like Earth, but feels completely wrong. The sky is familiar. The oceans are familiar. The continents look similar to the ones on our maps. But something is missing. Night falls, and the darkness is total. No soft silver glow, no quiet companion rising over the horizon. The moon is gone because in this timeline, it never formed or slipped away billions of years ago. At first, the world seems normal. The stars shine brightly. The waves crash on the shore. Life might even begin in the oceans, just as it did in our own timeline. But then things start to feel unstable. The ground beneath you is steady, but the world above your head is not. Without the moon, Earth's tilt on its axis has no anchor. In our real world, the moon acts like a stabilizer, keeping Earth's tilt steady at about 23 degrees. But here the tilt drifts. Sometimes it sits at a gentle angle, with mild seasons. Sometimes it leans so far that one pole spends half the year roasted under endless sunlight, while the other freezes in darkness. Then hundreds of thousands of years later, the tilt swings the other way. The seasons reshape themselves again. Winters become brutal and endless. Summers become scorching and lethal. Ice caps grow and melt on unpredictable cycles. Deserts expand, then vanish. Forests appear where frozen plains used to be. The climate never settles long enough for stable ecosystems to form. Every time life begins to adapt, the world changes again. Maybe tiny organisms still survive in the oceans. Maybe simple plants appear along the coasts. But complex life, creatures that require stable environments for millions of years, faces an impossible challenge. One bad tilt cycle and an entire species could vanish. Without the moon, the tides are tiny. Instead of huge daily sweeps that mix nutrients and pull life across the shallows, Earth gets weak ripples that barely shift the shoreline. In our world, the strong tides created tidal pools, where early organisms were pushed to survive both wet and dry conditions. These pools acted like training grounds for life, learning to crawl onto land. But on a moonless Earth, those training grounds barely exist. The push toward land becomes far more difficult and might never happen at all. Even the length of the day changes. In our world, the moon slows Earth's rotation over time. Without it, Earth spins faster and stays that way. Days might be only 10 or 12 hours long. That means short nights, rapid temperature swings and storms, shaped by a faster turning planet. Plants struggling to grow under these conditions face constant stress. Animals, trying to evolve steady sleep cycles, find no rhythm to lock onto. You might look around this alternate world and see life clinging to existence, but never thriving. Strange alien creatures may form, but their world shifts around them too violently for them to build stable lineages. Nothing ever gets the time needed to evolve intelligence or complex societies. Some scientists argue that without the moon, Earth might still have life, but it would be simple, scattered, and possibly doomed to collapse again and again. When you picture this world, you start to realize something important. The moon did not just light our nights. It steadied our seasons, shaped our tides, and slowed our rotation until Earth became a comfortable home for complex life. Without the moon, our world would be a place of endless climate chaos, a planet constantly resetting itself, a world where stability is rare and survival is a constant struggle. And in that world, we would almost certainly never exist. If you want to understand why Earth has been a cradle for life instead of a world of chaos, you have to look at the moon not as a light in the sky, but as a guardian. It has been quietly protecting our planet for billions of years. The moon does not roar, or flash, or make itself known. It stabilizes. It steadies. It holds Earth in place, like a gyroscope spinning beside us. And without it, everything we know about life and climate would collapse. The key to that protection is Earth's tilt. Earth is not straight up and down. It leans at about 23 degrees. That tilt creates seasons, shifting sunlight across the globe throughout the year. But a tilt is fragile. Without something to hold it steady, even tiny gravitational nudges from other planets would push it around. Over thousands of years, the tilt could swing wildly, from almost no tilt at all to angles so steep the poles would point nearly at the sunday. Those changes would transform the climate into a nightmare of extremes. But in our world, that never happened. For billions of years, Earth's tilt has stayed remarkably steady, drifting only slightly in gentle cycles that last tens of thousands of years. The reason is simple. The moon is the anchor. When Earth tilts, the moon pulls on the bulge around the equator, created by Earth's rotation. That pull resists the tilt, changing how fast it can wobble. The effect is powerful. It slows the chaotic motion that would otherwise twist Earth's axis into unpredictable angles. Scientists call this gravitational stability, but it is easier to picture it like this. Earth is a spinning top. Left alone, it wobbles. But place your hand close to it and steady it with the slightest touch, and the wobble softens. The moon is that steadying hand. Without it, Earth would behave like Mars, which has no large moon to stabilize it. Mars' tilt has swung from almost straight up to more than 40 degrees. When it tilts far enough, the poles melt and refreeze. The atmosphere thickens, then thins. Dust storms rage for months. Nothing stays stable long enough for life to flourish. Earth escaped that fate because of the moon. And the moon's stabilizing power did more than just protect the seasons. It created climate windows that remained consistent for millions of years. Those long, stable stretches allowed complex life to evolve and survive. Forests could spread, oceans could remain predictable, ice ages could come and go in cycles that life had time to adapt to. Even humans owe their existence to this stability. Our ancestors evolved in environments that shifted slowly enough for them to adapt generation by generation. Without the moon, those environments might have changed too quickly for humanity to emerge. Every time you see the moon hanging quietly in the night sky, you are looking at the reason Earth has a history instead of a constant restart. It kept the poles from wandering. It kept the climate from spiraling into chaos. It kept Earth gentle enough for life to take hold. The moon is not just a companion. It is Earth's stabilizer, a silent guardian that has watched over billions of years of evolution. Without it, our world would be unrecognizable. Without it, stability would be a luxury the planet could never afford. Look at any ancient civilization, and you will find the moon staring back at you from their stories, their rituals, and their calendars. Long before people understood gravity or resonance, or the violent history that almost left Earth moonless, they watched the glowing disk in the sky and felt that it meant something. They used it to guide their crops, track their festivals, and measure the passing of time. They gave it names, personalities, and powers. They treated it as a guardian, a messenger, a clock, and sometimes even a god. What none of them knew is that their entire culture was built around an object that almost never existed. When early humans first looked up at night, the moon was the brightest thing they could see. It changed shape with perfect regularity, waxing from a thin crescent into a full shining circle, then fading back again. That rhythm gave them a natural calendar long before anyone carved symbols into stone. A month became the time between full moons. Whole seasons were predicted by counting lunar cycles. Hunters planned their journeys around the light of the full moon. Farmers planted by its rise and fall. People who could not read the stars or the winds could still understand the moon. It was a reliable pattern in a world of danger. Cultures everywhere wove the moon into their stories. In ancient China, legends described a moon goddess watching over humanity. In Greece, the moon was a chariot riding across the night. In Africa, stories told of spirits dancing on the lunar surface. In the Americas, people saw animals, ancestors, or protectors etched across its face. The moon became a cultural anchor, just as it was a physical one. The rhythm of its phases shaped ceremonies from New Year festivals to harvest celebrations. Even today, many societies use lunar calendars for holidays that move gently across the modern year. But the deeper truth is stranger than any myth. All these traditions depend on a moon that physics almost denied us. If the early resonance with the sun had lasted longer, the moon would have escaped into deep space, leaving Earth dark and unstable. If Earth's magma ocean had cooled too quickly or too slowly, the moon might have crashed back down or drifted too far. If Jupiter and Venus had shifted Earth's orbit by even a fraction more, the resonance could have torn the moon loose. In those alternate timelines, humanity would never have looked up at night and seen a glowing companion. There would be no lunar calendars, no stories written in starlight, no myths about gods on silver chariots. Nights would be darker. Navigating the oceans would have been far harder for early sailors. Ancient cities might have grown differently without the moon's gentle light guiding them. Even human imagination might have taken another shape without the moon's presence, inspiring questions about the sky. When you realize how close Earth came to losing the moon, every ancient carving and every lunar myth feels like evidence of incredible luck. Our cultures grew beneath a moon that survived a billion-year struggle to stay with us. People looked up and wrote poetry, never knowing that the object inspiring them had passed through gravitational chaos that should have torn it away. The moon we celebrate in stories is more than just a symbol. It is a reminder that entire human cultures blossomed under a sky that almost never had a moon at all. If you stand outside on a calm night and look at the moon, it seems completely still. It hangs over the world like a lantern that has always been there and always will be. But that is an illusion. The moon is moving. It is drifting away from Earth right now at the pace your fingernails grow. Every year, it gets a few centimeters farther. It is such a tiny change that no one can see it, but telescopes and lasers can. Scientists send laser pulses to mirrors Apollo astronauts left on the surface and measure the time it takes for the reflection to return. Those numbers do not lie. The moon is leaving us very slowly, but definitely. The strange part is that this slow drift is not something new. It has been happening for billions of years. But what most people do not realize is that the rate of drift has not always been gentle. Today the moon is far enough away, and Earth's rotation is slow enough that the system is stable. There is no danger of escape. Earth pulls on the moon too strongly now for anything dramatic to happen. But if you rewind far enough back in time, you enter a world where the drift was not calm at all. It was violent, unstable, and filled with moments when the wrong combination of gravity and timing could have changed everything. The reason the moon keeps drifting outward comes down to tides. As Earth rotates, the oceans bulge toward the moon. Those bulges do not line up perfectly with the moon. They sit slightly ahead because Earth spins faster than the moon orbits. Those forward-leaning bulges pull on the moon and give it energy, and the moon uses that energy to climb into a higher orbit. It is a constant exchange. Earth slows, the moon climbs, and the distance between them grows. But here is the important part. In the ancient past, the tides were much stronger. Earth spun much faster. The oceans were deeper and often filled with molten rock. So the bulges dragged harder. They shoved more energy into the moon. They pushed it outward at rates far beyond today. In some simulated timelines, the moon gained energy so quickly that it passed into zones where the sun's gravity almost stole it. The difference between a safe drift and a runaway drift came down to how fast Earth slowed and whether certain resonances kicked in at the wrong time. Those chaotic epochs are long gone. Earth's rotation has slowed to a safe rhythm. The tides are weaker, and the moon has moved far beyond the dangerous resonant zones. Now, even though it continues to drift outward, the rate is too gentle to ever threaten escape. Eventually, after billions more years, the drift will stop when Earth's rotation slows enough to match the moon's orbital period. Earth and the moon will become tidally locked to each other, both showing the same face forever. But long before that, the sun will swell into a red giant and erase both worlds from existence. So no, the moon will not leave us. It cannot now. Yet the fact that it once could have, and almost did, is what makes today's calm sky so strange. When you see the moon drifting away inch by inch, you are watching the end of a long story filled with danger that no human ever witnessed. The peaceful drift we see now is the last quiet echo of a violent past where Earth and the moon nearly parted ways forever. When scientists say the moon nearly escaped, they are not exaggerating. They mean it in the most literal way possible. If you could rewind the early Earth-Moon system and change even the tiniest detail, the outcome could shift from our familiar sky to a world with no moon at all. The closeness of that near loss is almost impossible to wrap your mind around because it was not a dramatic single event. It was a sensitivity problem, a system so finely balanced that almost anything could have pushed it off course. To understand how close we came, you have to picture the early Earth spinning faster than any planet has a right to spin. A day lasted only a few hours. That speed created monstrous tides in the magma oceans. Those tides pumped huge amounts of energy into the moon. When the moon reached certain distances, that extra energy pushed it into resonant zones where the sun's gravity got involved. That is where danger lived. The simulations showed that if Earth's early rotation had been only a few % faster, the tides would have been so strong that the moon would have been pushed outward much more quickly. That faster drift would have placed the moon in the evection resonance at a slightly different time, and that timing change was enough to turn a dangerous resonance into a lethal one. In that version of history, the sun would tug at the moon at the perfect moment, again and again. The moon's orbit would stretch farther each cycle until Earth could not pull it back. Escape would follow. The moon would become a wandering object drifting through space with no reason to look back. But slowing Earth down just a little created a completely different problem. If Earth's rotation had been only slightly slower during the first tens of millions of years, the tides would have been weaker. Weak tides would have failed to give the moon enough outward push. It would have remained too close to Earth for too long, where the gravitational forces were brutal. In many simulations like this, the moon spiraled inward. It began dipping into lower orbits, where tidal heating tore at its surface. Eventually, the inward spiral accelerated until the moon collided with Earth. That collision would have melted the crust all over again and erased any chance of a stable climate for hundreds of millions of years. The depth of Earth's early oceans also mattered in ways that feel almost absurd. Changing the average depth by just a few hundred meters changed how strong the tides were. A slightly deeper magma ocean could amplify the tidal bulges enough to push the moon into unstable ground. A slightly shallower ocean could dampen the tides too much and pull the moon inward. It was such a delicate balance that even small differences in mineral composition could strain the system. Temperature mattered too. If the mantle cooled faster or slower by only a few %, the internal tides changed. That affected how quickly Earth's rotation slowed and how much energy the moon absorbed. A few % does not sound like much, but in those simulations a few % decides whether the moon ends up in a safe orbit or tears free and drifts away forever. The sensitivity was so extreme that some researchers compared the early Earth-Moon system to balancing a pencil on its point. You can do it for a moment if you are lucky, but shift the air or the table, or even breathe too hard, and the pencil falls. Our universe happened to be one of the rare cases where everything lined up perfectly. Earth slowed at the right rate. The oceans cooled at the right speed. The resonances broke at the right moments. That is how close nearly was. Not thousands of kilometers, not millions of years. Just small, delicate differences in rotation, in water depth, in temperature. A few % here or there, and tonight the sky above you would be empty. When scientists began studying planets around other stars, they expected to find moons everywhere. Our solar system is full of them. Jupiter alone has dozens. Saturn has a moon bigger than Mercury. Even tiny dwarf planets have companions, so it seemed obvious that moons should be common across the galaxy. But as the data came in, something strange happened. We kept finding planets, thousands of them. Hot giants skimming their stars, frozen worlds drifting in dark orbits, rocky planets spinning in habitable zones. But we did not find moons. Not the big ones, anyway. Not moons like ours. And the more scientists looked, the more they began to suspect something astonishing. Moons as large and stable as Earth's might be rare, because the early dance that created and preserved them is incredibly fragile. The same instabilities Earth barely survived might have destroyed countless moons around other worlds. Picture an exoplanet forming in another system. A giant impact hits it just like Theia struck early Earth. A moon forms from the debris and begins its outward drift. At first everything looks fine, but the planet spins too quickly or too slowly. Or the molten oceans stay hot for too long. Or the nearby giant planet tugs just a little harder than Jupiter tugged on Earth. Suddenly the moon drifts into a resonance that grows too strong. The star pulls in perfect rhythm with the moon's orbit. The orbit stretches, the energy climbs. In a few million years, the moon escapes completely, drifting into interplanetary space. The planet is left alone, without a stabilizer, without tides strong enough to shape its coasts or its climate. Life might still form, but the environment will be wild and unstable, so the system moves on. The moon becomes just another lost object, catalogued in silence. In other systems, the disaster goes the other way. The moon formed normally, but the tides are too weak to push it outward. The planet cools too quickly. The crust hardens too soon. Without enough drag, the moon stays close. Too close. The inward spiral begins. At first it is slow, then faster, as tidal friction tears both worlds apart. The moon eventually crashes into the planet, forming a molten ocean where continents might have formed. Any chance for stable climates disappears in one catastrophic moment. The more researchers simulate these early systems, the more they realize how many things have to go exactly right. The rotation must slow at the right speed. The resonance with the star must break before it becomes dangerous. The tides must be strong enough to push the moon outward, but not so strong that they fling it away. And the presence of other planets must not pull the system into chaos. That is a lot of luck for any world to have. When scientists model thousands of exoplanet systems, they see that many likely lost moons during their early chaotic periods. Some moons were thrown into space. Others were shattered. Some may have been stolen by their stars. Some may still be drifting in orbits that make them nearly impossible to detect. And that brings us back to Earth. Our moon is not just large. It is almost impossibly large compared to our planet. It occupies a stable orbit that required an unbroken chain of lucky escapes. Not all worlds will win that kind of cosmic lottery. When we look at distant systems and fail to see moons, we might be witnessing the aftermath of dances that went wrong. Giant impacts that formed moons only to lose them. Or planets that never had the stability needed to keep them. So when you see the moon shining in the night sky, you are not just seeing Earth's companion, you are seeing a survivor. A rare moon in a galaxy where many worlds may have lost theirs before life ever had a chance to wonder where they went. If you ever feel like the universe is too big to care about tiny chances, you only have to look at the moon to realize how wrong that is. Our entire existence depends on a chain of accidents so unlikely it feels almost impossible. A world-ending collision that somehow did not end the world. A molten planet that cooled at just the right speed. A set of gravitational rhythms that could have torn the moon away but broke at the last possible moment. Every step in our story is a reminder that cosmic luck is fragile, and every survival we take for granted was almost a disaster. Start with the giant impact itself. A Mars-sized world slammed into early Earth with enough force to melt both bodies. Impacts like that usually end in total destruction. Many planets never recover from such a hit. They become barren molten rocks or lose so much mass they never form oceans or continents again. But our Earth took the blow in the narrowest way possible. It survived without shattering. It spun fast enough to create massive tides, but not so fast that it tore itself apart, and the debris flung into space did not drift away or fall back randomly. It gathered into a disk and formed the moon. 1% different energy, and none of this happens. Then the second miracle followed. The moon began to drift outward from Earth. At first this was just physics. Tides slowed Earth and lifted the moon. But deep inside, those early tides were hidden dangers. Resonances waited like traps. If Earth's rotation had slowed slightly faster, the moon would have drifted outward too quickly and fallen into the grip of the Sunday. If Earth had cooled slightly slower, the tides would have pumped too much energy into the moon and flung it away. If the early oceans were deeper, or if the crust formed too fast, the balance would shift and the moon would spiral inward. That is how thin the line was. The moon was almost lost during multiple epochs, and each time escape was prevented by tiny differences. A slight mismatch in timing, a slight shift in temperature, a slight wobble in Earth's tilt. Even the presence of Jupiter and Venus played a role. Their gravity tugged on Earth in small repeating patterns. In some simulated timelines, those tugs were enough to push the moon into trouble. In our timeline, they were not. Their rhythms slipped out of sync at the right moment, and the dangerous resonance faded. It is strange to think about. The orbits of distant planets help decide whether Earth would have a moon at all. And then there is the biggest miracle of all. The moon stayed long enough to steady Earth's tilt. Without it, Earth would wobble like Mars, tumbling through climate cycles too unstable for complex life. Our seasons would shift wildly. Ice ages could appear out of nowhere. Continents would freeze and thaw in unpredictable cycles. Evolution might never get a chance to build forests or oceans rich with life. Humanity would never appear because the world would never sit still long enough for us to evolve. Every piece of Earth's story rests on fragile luck, a lucky impact, a lucky orbit, a lucky break in a deadly resonance, a lucky balance between tides and rotation. When you think about all the ways things could have gone wrong, it becomes almost unbelievable that things went right at all. And yet here we are, living on a planet that should not have survived its beginning, looking up at a moon that should not still be here, walking under a sky shaped by moments of cosmic luck, so precise they feel like the universe was threading a needle, not because it wanted to, not because it cared, but because sometimes, even in the cold logic of physics, the narrowest possible path is the one reality ends up taking. If the story of the moon teaches us anything, it is that the universe does not bend to our plans. It does not slow down to ask what we want. It does not wait for our permission before shaping the conditions we are born into. The early Earth had no control when a wandering world smashed into it. It had no control when the molten tides nearly flung the moon into space. It had no control when the sun tugged at the wrong rhythm, or when Jupiter and Venus twisted its orbit by the smallest amount. Everything that determined whether the moon stayed or vanished happened long before life appeared. Yet those uncontrollable events shaped everything about us. They decided our seasons. They set the length of our days. They stabilized our climate. They created tides that shaped shorelines where early life crawled onto land. They kept Earth steady enough for forests to grow and species to evolve. They gave humans a moon that inspired stories and guided generations. None of it was chosen. None of it was planned. All of it mattered. That realization hits hard because it mirrors the truth we face today. We are used to thinking we are in control. We plan our days and build our cities and act like the future will follow whatever path we draw for it. But the moon's story is a reminder that the biggest forces in our lives often begin outside our reach. We cannot control where we were born, or what century we live in, or what kind of planet we inherit. We did not choose a world warming under human activity. We did not choose rising seas or stronger storms or shrinking ecosystems. But here is the difference. Early Earth had no choices. We do. The forces shaping the moon's fate were blind and automatic. They obeyed physics without hesitation. They followed resonances and energy transfers with no room for intention. But humans are not trapped in that same kind of system. We cannot control the orbit of the moon. We cannot rewrite the past. But we can decide what to do with the conditions we are given. The moon almost leaving Earth is a story about powerless beginnings. But humanity does not live in that beginning. We live in the aftermath. We live in a world that survived its chaos and handed us the most stable climate window in billions of years. What we do with that stability is up to us. When we look back at the moon's near escape, it should not just make us feel lucky, it should make us feel responsible. The universe will always be bigger than us. It will always throw storms and impacts and resonances across the sky, but none of those forces decide how we treat each other, how we protect our planet, or how we prepare for the future. The moon teaches us that we are born into a world shaped by events we never controlled, but it also teaches us something more important. Survival depends on what we do next. Earth could not choose to hold on to the moon, but we can choose how to hold on to the only world we have. Go outside on a quiet night and look up. Not quickly, not in passing. Really look. The moon hangs there like it always has, glowing with a calm that feels eternal. But once you know its story, that calm becomes something else. You are not looking at a peaceful object. You are looking at a survivor. A world that lived through chaos and fire and gravity, trying again and again to pull it away from us. You are looking at something that beat the odds, something that almost never made it into your sky at all. When you stare at it long enough, you begin to feel the weight of its history. 4.5 billion years ago, that light you see now did not exist. The moon was still part of Earth until a wandering planet struck and tore it free. The sky was molten. The tides were monstrous. The planet shook with every orbit. The moon could have fallen back into Earth and ended everything. It could have escaped into the cold black nothing between worlds. But it did neither. It survived. Millions of years later, when the sun tugged in perfect rhythm and almost slung the moon into space, the resonance snapped just in time. The orbit steadied. The danger passed. The moon survived again. When Jupiter and Venus twisted Earth's path and nearly pushed the system into chaos, the timing slipped out of sync at the last possible moment. The moon survived again. When impacts blasted its surface, carving scars still visible today, some of those hits nudged its orbit in risky directions. But each time the moon held on to the narrow lane that kept it close to Earth. The moon survived again. You stand there under that ancient light, knowing the sky above you is the result of near misses layered on top of near misses. 1,000 cosmic coin flips, and somehow they all landed the one way that kept the moon here. If even one of them had fallen differently, there would be no familiar glow above you, no tides shaping our coasts, no steady seasons guiding the evolution of life. There might be no forests, no oceans full of complexity, no humans wondering how any of this happened. The moon is not just a companion. It is a reminder that existence itself can be fragile, that everything you know came from a universe that almost had a different ending. And yet here it is, still rising and setting, still pulling at the ocean, still lighting the night as if it never struggled at all. When you look at the moon after knowing its story, something changes. You stop seeing a simple circle of light and start seeing a survivor that made it through fire and chaos and the pull of the Sunday. You start seeing a world that beat 1,000 chances to vanish. You start seeing the truth. Our sky is not guaranteed. It never was. The moon is still here for now, and that alone is a miracle written across billions of years. So you look up one last time and understand what you are really seeing, the survivor in the sky.